Hi everybody, welcome back to the Feynman technique. Today we'll be evaluating this integral that I got off of the channel QN cubed. And this one was challenging for me. I've been working on this one for a little while, and it just wasn't clicking using Feynman integration. Of course, he evaluated it using contour integration. I will link to his video in the description. And I will also link to my video showing this. We're going to need this to solve that. That's that the sum of the reciprocals of the odd cubes is equal to pi squared over 8. In other words, this 1 plus 1/9 plus, let's see, 1/25 plus 1/49 forever, and that equals pi squared over 8. And I'll give a very brief explanation of why that's true. If we start from here, that the sum from n equals 1 to infinity of 1 over n squared, that's the sum of the reciprocals of the squares, which I will also link to in the description. That is equal to pi squared over 6. So if you take this and then multiply both or divide both sides by 4 and then subtract the 2, you will get this. So go ahead and try that for yourself, or go ahead and watch the video that I'll link to. Alright, so let's get started with our problem. Alright, now the thing that really tripped me up here was I wanted to break this up, or I wanted to represent this using Taylor series, because I saw this this natural log squared x in the numerator. And I know that usually, if you're using Feynman integration, what you want to do is just replace that with an x to the t and then take two derivatives. And then I tried to break it up using Taylor series. And I wasn't successful because the Taylor series that I wanted to use did not converge on 0 to infinity. It's only good from on the interval -1 to 1. But then I realized we could do this. We can break this up into two separate integrals. So we can write this as I is equal to the integral from 0 to 1 of natural log squared x. And I'm going to start writing this square root of x as x to the -1/2 natural log squared x over 1 minus x squared dx plus the integral from 1 to infinity of x to the -1/2 natural log squared x over 1 minus x squared dx. All right. And then on this integral right here, we can use the substitution that x is equal to 1 over u. Therefore, dx is equal to -1 over u squared du. All right, so let's rewrite this integral using that. All right, and I'm going to rewrite the entire thing. So making that substitution, we have that I is equal to the integral from 0 to 1 of x to the -1/2 natural log squared x over 1 minus x squared dx, and then applying this substitution to the integral from 1 to infinity will give us, well, let's see, we'll have the integral. If our lower bound is 1, it will stay 1. If our upper bound is infinity, it will be 0. X to the negative 1/2 will become u to the 1/2. Natural log squared x will become natural log squared of 1 over u, which is natural log squared of negative u, which is negative, which is the natural log, negative natural log squared of u, which is just natural log squared u. And then on the denominator, we will have 1 minus 1 over u squared. Then for our dx will become negative 1 over u squared du. We'll use the negative sign to switch the bounds. And we'll distribute the u squared inside our denominator right there. This will become a minus 1. This will become a u. And you'll notice that u minus 1 squared is the same as 1 minus u squared. So we'll write it like that. 1 minus u squared du. There we go. And now I'm just going to change all these u's back to x's. So we have, so we're working with the same variable, although it doesn't matter. There we go. All right. Okay, now we can reparameterize this. We can create a function of t that's equal to the integral from 0 to 1 of x to the t over 1 minus x squared dx. And you'll notice that this integral right here actually does not converge for any values of t. This integral would be divergent no matter what real number you plug in for t. And we're not going to be using complex numbers, so that's not where I'm going with this. But we don't actually care about the actual value of f of t. We care about the behavior of its second derivative, because that's where we recover the natural log squared x. And it's 100% true that you can have a function of x or t or whatever that is divergent and whose first derivative is also divergent, but whose second derivative is actually nicely behaved. And I'll just give you an example. Let's say we have f of t is equal to the limit as a goes to infinity of x squared plus ax plus a. You'll see that this function, the function itself, is divergent. I mean, if you let a go to infinity, the value, no matter what you put in for x, is going to be infinity. However, if you took two derivatives of this, you would get f double prime of t is equal to the limit as a goes to infinity of 2. So we don't even care about a anymore. The second derivative is simply equal to 2. So there's an example of a function that is divergent, whose derivative is also divergent, but whose second derivative is not. So those types of functions do exist. All right. So anyway, there's our f of t, and I'm not going to go through the process of taking the first derivative. I'm just going to jump right to the second derivative, because that's what we're really interested in. So f double prime of t is equal to the, and it's very easy to take derivatives with respect to t of this thing using the Leibniz rule. 0 to 1 of x to the t natural log squared x, and that natural log squared x comes from taking two derivatives of this with respect to t, over 1 minus x squared dx. All right. Now you'll notice that if we evaluate our f double prime at the point 1/2, and then add it to f double prime evaluated at negative 1/2, we'll get I. So I'll write that right here, that if we take f at double prime at 1/2 plus f double prime at negative 1/2, that's going to equal our original integral. Okay, so now we need to break out Taylor series to re-represent our original f of t. And I've used the fact that 1 minus x, 1 over 1 minus x is equal to the sum from is equal to the sum from 0 to infinity of x to the n. But I've never shown the Taylor series representation for 1 over 1 minus x squared. But really quickly I'll derive that. So if we start with the fact that the sum from n equals 0 to infinity of x to the n is equal to 1 over 1 minus x on the interval negative 1 to 1. And I think one of these bounds is actually included. I always forget which one it is though, but this is definitely true. Then it's a simple matter of taking a derivative on both sides. So we just have that the sum from n equals 0 to infinity of n x to the n minus 1 is going to be equal to 1 over 1 minus x squared, because taking the derivative with respect to x of this will give us negative this to the negative 2 times negative 1. In other words, 1 over 1 minus x all squared, which is exactly what we have here. All right. So we will be using that now. So our f of t is equal to, let's see, we'll have the integral from 0 to 1, and we'll still have the x to the t. But then in place of 1 minus x all squared, we will have the sum from n equals 0 to infinity of n x to the n minus 1, and then dx. We'll bring this x to the t inside the sum to give us n plus t minus 1. We will switch the summation and integration signs. So this will give us, this is going to be the integral from 0 to 1. And on the outside, we'll have the sum from n goes from 0 to infinity. We can bring out the n. And integrating this will give us 1 over, evaluating this integral will give us 1 over n plus t. And you'll also notice that this function is divergent for all values of t also, which makes sense because our original f of t was divergent as well. So it's a good thing we're not actually interested in any specific values of this, because we wouldn't be able to obtain any. And you'll also notice that we could, if we wanted to, we don't even need to include the n equals 0 term, because the first term of this is simply going to be 0, because it's going to be 0 over t, which is 0. So we could just replace that with an n equals 1. I'm not going to do that yet, though. All right, what we're going to do right now is jump two derivatives of our f of t. So f double prime of t is now equal to, let's see, we're going to take two derivatives of this thing with respect to t. So we'll definitely, we're still going to have the n on the top, and this is going to be n plus t cubed. So originally we'd recover a negative 1, and then we'd recover a negative 2. So that's just going to be 2. And then we're still going from n equals 0, which again we don't technically need to include. And it's going up to infinity. All right. So now what do we do? Well, we kind of have it now. We have the function for which we will be plugging in value, for which we will plug values into. So let's just, I'm going to rewrite this f double prime at 1/2 plus f double prime at negative 1/2 is equal to I over here. Actually, we'll just do this. I is going to be equal to, and now I'm actually going to plug in 1/2 into this equation right here. So we're going to have 2 sum from n equals 0 to infinity of n over n plus 1/2 cubed. And then plus 2 times the sum from n equals 0 to infinity of n over n minus 1/2 all cubed, right? Because that is f double prime evaluated at 1/2, that's right here, plus f double prime evaluated at negative 1/2, that's right here. Okay, so now the first thing I think I want to do is we're going to perform a familiar manipulation on this one right here. We are going to advance our index by 1, and then we will subtract 1 from all the n's inside the sum. So this is going to be the sum from n equals 1 to infinity of n minus 1 over n minus 1/2 all cubed. Now you see we can almost bring these two sums together. Not quite though, because we have this n equals 0 term, but remember that n equals 0 term right here is simply 0, so we don't even need it. We can just start this thing at n equals 1. And now we have the exact, almost the, well, we have the same denominator and we have the same interval. So we can bring them together by just adding the numerators together. So this will become 2n minus 1. And we can get rid of this second sum right here. Okay. Great. So now I think what I want to do is, there's probably a quicker way to do this, a more direct way, but I'm going to factor out a 2 in the numerator right here. That's going to give us n minus 1/2, and this is going to become a 4. All right. Now you'll notice that we have something over the same something cubed, so that's just going to be 1 over the something squared. Okay, well, we're getting close now. What I'd like to do is change this to a 2n minus 1. And how you can do that is multiplying the top and the bottom by 4. So we can have this as 4 over 2n minus 1 all squared. All right, now we can bring this 4 out as a 16, and we are done. Because we started with this, the sum from n equals 1 to infinity, which we have, of 1 over 2n minus 1 squared is equal to pi squared over 8. 16 times that is going to give us 2 pi squared. And there you go. Hope you enjoyed that.